You might have seen robots do plenty of stuff from cleaning to building. However, one thing that a robot has trouble doing is making a pizza. Yes, for a robot, working with a deformable object like dough is tricky because the shape of dough can change in many ways, which are difficult to represent with an equation. Plus, creating a new shape out of that dough requires multiple steps and the use of different tools. It is especially difficult for a robot to learn a manipulation task with a long sequence of steps where there are many possible choices, since learning often occurs through trial and error. Researchers at MIT, Carnegie Mellon University and the University of California at San Diego have come up with a better way. They created a framework for a robotic manipulation system that uses a two-stage learning process, which could enable a robot to perform complex dough manipulation tasks over a long time frame. A teacher algorithm solves each step the robot must take to complete the task. It is a trajectory optimization algorithm that can solve short horizon tasks where an object's initial state and target location are close together. The teacher algorithm uses the information in the simulator to learn how the dough must move at each stage, one at a time, and then outputs those trajectories. Then it trains a student machine learning model that learns abstract ideas about when and how to execute each skill it needs during the task, like using a rolling pin. It learns to imitate the actions of the teacher. As inputs, it uses two camera images, one showing the dough in its current state and another showing the dough at the end of the task. The neural network generates a high-level plan to determine how to link different skills to reach the goal. It then generates specific short horizon trajectories for each skill and sends commands directly to the tools. With this knowledge, the system reasons about how to execute the skills to complete the entire task. The researchers show that this method, which they call devise, can perform complex manipulation tasks in simulations like cutting and spreading dough or gathering pieces of dough from around a cutting board, while outperforming other machine learning methods. Beyond pizza making, this method could be applied in other settings where a robot needs to manipulate deformable objects, such as a caregiving robot that feeds, bathes, or dresses someone elderly or with motor impairments. The author Lee states, "This method is closer to how we humans plan our actions. When a human does a long horizon task, we are not writing down all the details. We have a higher level planner that roughly tells us what the stages are and some of the intermediate goals we need to achieve along the way, and then we execute them." Devise was able to outperform popular techniques that rely on reinforcement learning, where a robot learns a task through trial and error. In fact, devise was the only method that was able to successfully complete all three dough manipulation tasks. Interestingly, the researchers found that the student neural network was even able to outperform the teacher algorithm. The researchers intend to improve the performance of devise by using 3D data as inputs instead of images that can be difficult to transfer from simulation to the real world. They also want to make the neural network planning process more efficient. Related to robots, engineers at the University of California, San Diego have developed a low-cost, low-power technology to help robots accurately map their way indoors, even in poor lighting and without recognizable landmarks or features. The technology consists of sensors that use Wi-Fi signals to help the robot map where it's going. It's a new approach to indoor robot navigation. Most systems rely on optical light sensors such as camera and lidars. In this case, the so-called Wi-Fi sensors use radio frequency signals rather than light or visual cues to see, so they can work in conditions where cameras and lidars struggle, in low light, changing light and repetitive environments such as long corridors and warehouses. And by using Wi-Fi, the technology could offer an economical alternative to expensive and power-hungry lidars, the researchers noted. The researchers built their prototype system using off-the-shelf hardware. At the start, the Wi-Fi sensors are unaware of robots' location and where any of the Wi-Fi access points are in the environment. Figuring that out is like playing a game of Marco Polo. As the robot moves, the sensors call out to the access points and listen for their replies, using them as landmarks. The key here is that every incoming and outgoing wireless signal carries its own unique physical information that can be used to figure out where the robot and access points are in relation to each other. Algorithms enable the Wi-Fi sensors to extract this information and make these calculations. As the call and response continue, the sensors pick up more information and can accurately locate where the robot is going. The researchers tested the technology on a floor of an office building. They placed several access points around the space and equipped the robot with the Wi-Fi sensors as well as a camera and a lidar to perform measurements for comparison. In these tests, the accuracy of localization and mapping provided by the Wi-Fi sensors was on par with that of the commercial camera and lidar sensors. Meanwhile, researchers at the Department of Energy's Oak Ridge National Laboratory are teaching microscopes to drive discoveries with an intuitive algorithm that could guide breakthroughs in new materials for energy technologies, sensing and computing. Functional materials are responsive to stimuli such as heat or electricity and are engineered to support both everyday and emerging technologies, ranging from computers and solar cells to artificial muscles and shape memory materials. Their unique properties are tied to atomic structures and microstructures that can be observed with advanced microscopy. However, the challenge has been to develop efficient ways to locate regions of interest where these properties emerge and can be investigated. Scanning probe microscopy is an essential tool for exploring the structure-property relationships in functional materials. Instruments scan the surface of materials with an atomically sharp probe to map out the structure at the nanometer scale, the length of 1/1000th of a meter. They can also detect responses to a range of stimuli, providing insights into fundamental mechanisms of polarization switching, electrochemical reactivity, plastic deformation, or quantum phenomena. Today's microscopes can perform a point-by-point scan of a nanometer square grid, but the process can be painstakingly slow, with measurements collected over days for a single material. Scientists have turned to machine learning and artificial intelligence to overcome this challenge, but conventional algorithms require large human-coded datasets and may not save time in the end. For a smarter approach to automation, the ORNL workflow incorporates human-based physical reasoning into machine learning methods and uses very small datasets, images acquired from less than 1% of the sample, as a starting point. The algorithm selects points of interest based on what it learns with the experiment and on knowledge from outside the experiment. As a proof of concept, a workflow was demonstrated using scanning probe microscopy and applied to well-studied ferroelectric materials. Ferroelectrics are functional materials with a reorientable surface charge that can be leveraged for computing, actuation, and sensing applications. Scientists are interested in understanding the link between the amount of energy or information these materials can store and the local domain structure governing this property. The automated experiment discovered the specific topological defects for which these parameters are optimized. Results were faster by orders of magnitude than conventional workflows and represent a new direction in smart automation. Speaking of AI, predicting how climate and the environment will change over time or how air flows over an aircraft are too complex even for the most powerful supercomputers to solve. Scientists rely on models to fill in the gap between what they can simulate and what they need to predict. But as every meteorologist knows, models often rely on partial or even faulty information that may lead to bad predictions. Now, researchers from the Harvard John A. Paulson School of Engineering and Applied Sciences are forming what they call intelligent alloys, combining the power of computational science with artificial intelligence to develop models that complement simulations to predict the evolution of science's most complex systems. In their first paper, the researchers combined reinforcement learning with numerical methods to compute turbulent flows, one of the most complex processes in engineering. Reinforcement learning algorithms are the machine equivalent to B.F. Skinner's behavioral conditioning experiments. Skinner, the Edgar Pierce Professor of Psychology at Harvard from 1959 to 1974, famously trained pigeons to play ping pong by rewarding the avian competitor that could peck a ball past its opponent. The involved reinforced strategies like cross-table shots that would often result in a point and a tasty treat. In the intelligent alloys, the pigeons are replaced by machine learning algorithms or agents that learn by interacting with mathematical equations. Using this process, the researchers were able to predict challenging turbulent flows, interacting with solid walls such as a turbine blade more accurately than current methods. In their second paper, they used machine learning algorithms to accelerate predictions and simulations of complex processes that take place over long periods of time. Take morphogenesis, the process of differentiating cells into tissues and organs. Understanding every step of morphogenesis is critical to understanding certain diseases and organ defects, but no computer is large enough to image and store every step of morphogenesis over months. By using these algorithms, the researchers demonstrated that they can generate predictions thousands to 1,000,000 times faster than it would take to run the simulations with full resolution. Because the algorithms have learned how to compress and decompress the information, they can then generate a full representation of the prediction, which can then be compared to experiments. The researchers demonstrated this approach on simulations of complex systems, including molecular processes and fluid mechanics. Co-author Bai states, there is a huge range of applications because every engineering system from offshore wind turbines to energy systems uses models for the interaction of the flow with the device, and we can use this multi-agent reinforcement idea to develop, augment and improve models. What are your thoughts on these technologies? Do let us know in the comments.